The more important thing that I want you to notice when you're looking at this, this wave equation for a 1sh atom is the fact that if you look at the angular component of the wave function, you'll notice that it's a constant. It doesn't depend on theta, it doesn't depend on phi. No matter where you specify your electron is in terms of those two angles, it doesn't matter. The angular part of your wave function is going to be the same. So what does that mean for us? Well, essentially what that tells us is that these s orbitals are spherically symmetrical. That should make sense, right? Because they're only dependent on r, how far you are away from the nucleus in terms of a radius. They don't depend at all on those two angles. They're independent of theta and they're independent of phi. So what I'm showing in this picture here is just an electron cloud that you can see. Think of it as a probability density plot. And what here is just a graph of the 1s wave function going across some radius defined this way. And you can see that the probability, well, this is the wave function, so we would have to square it and think about the probability. So this squared, and my light is gone again, at the origin is going to be a very high probability, and it decays off as you get farther and farther away from the nucleus or from the center, and that's independent of the angle. So let's look at these probability plots of different s orbitals here. And up top here, it just comes and goes. Okay, so up top here we have the probability density plot. And what you can see is what I just said. Very high probability density in the nucleus, decays as you go out. And what is plotted below is the actual wave function. So you can see it starts very high and then decays down. More interesting is to look at the 2s wave function. So if we look at the bottom here and the actual plot of the wave function, we see it starts high, very positive, and it goes down and it eventually hits 0 and goes through 0 and then becomes negative and then never quite hits 0 again, although it approaches 0. So at this place where it hits 0, that means that the square of the wave function is also going to be 0, right? So we can see, if we look at the probability density plot, we can see there's a place where the probability density of finding an electron anywhere there is actually going to be 0. So we can think of a third case where we have the 3s orbital. And in the 3s orbital, we see something similar. We start high, we go through 0, where there will now be 0 probability density, as we can see in the density plot graph. Then we go negative, and we go through 0 again, which correlates to the second area of 0 that shows up also in our probability density plot. And then we're positive again and approach 0 as we go to infinity for r. So what this means is that when we're looking at an actual wave function, we're treating it as a wave, right? So waves can have both magnitude, but they can also have a direction, so they can be either positive or negative. So for example, if we were looking at the actual wave function, we would say that these parts here have a positive amplitude, and in here we have a negative amplitude. And when we're looking at the probability density graphs, it doesn't make a difference. It's okay. It has no meaning for our actual plot there because we're squaring it, so it doesn't matter whether it's negative or positive. All that matters is the magnitude. But when we're thinking about actual wave behavior of electrons, it's just important to keep in the back of our head that some areas have positive amplitude and some have negative. So we'll talk about this more when we get into p orbitals, and bonding is where it's going to become an issue. So I just want to kind of introduce that idea here, because if we think about wave behavior of electrons and we're forming bonds, then what we have to do is have constructive interference of two different electrons, right? To form a bond, we want to add together those probabilities. So we want to have constructive interference to form a bond, whereas if we had destructive interference, we would not be forming a bond. So that's where you have to think about whether it's positive or negative. You don't have to think about it right now, but you might have heard in high school talking about p orbitals, the phase. Sometimes you mark a p orbital as being a plus sign or a negative sign. Did any of you do that in high school at all? A little bit, yeah. So that's having to do with the actual wave function. So that'll become more relevant later, bonding, actually quite a couple lectures down the road. But I just want to introduce it here while we do, in fact, have the wave function plots up here.